My name is Esteban Arroyo. I'm a data analysis and digitalization expert at Covestro's headquarters in Leverkusen, Germany. I have a background in industrial and electrical engineering and process automation.
Hi, I'm Philipp Frenzel. I'm a process technology expert. I'm also located in Leverkusen, and my background is chemical engineering, focusing on process design and optimization.
Our company, Covestro, is a world-leading chemical manufacturer of high-tech polymers. We have 16,800 employees and over 30 production sites worldwide. Our portfolio mainly comprises of polyurethanes, often used in insulation and foams in cars and houses, polycarbonates, primarily used in the automotive, electronics, and medical industries, and coatings, largely used in vehicles, buildings, and sports apparel. Last year, Covestro had a total revenue of 14.6 billion euro, and since March 2018, we are part of the DAX index as one of the 30 biggest companies in Germany. As part of Covestro's effort to remain a global leader in the high-tech materials field, we have launched the company-wide digital transformation program, Digital at Covestro. Digital at Covestro seeks to leverage the benefits of digital technologies such as advanced analytics, machine learning, social networks, and e-commerce in three main areas, namely digital operations, customer experience, and business models. Of particular interest for this talk is the area digital operations. Here, the focus of digitalization has been set on leveraging our vast amount of process data to increase the reliability, efficiency, and safety of our manufacturing processes. This should be achieved by devising methods to collect, structure, visualize, and analyze data in order to predict process behaviors and enable thereby useful use cases such as predictive maintenance and process optimization. Aligned with this vision, we have launched the ProDavis Digitalization Initiative. ProDavis, which stands for Process Data Analysis and Visualization, is composed by a multidisciplinary group of engineers from different Covestro divisions with expertise in key areas such as process design, simulation, advanced process control, data science, OT, and IT. The goals of ProDavis include to enable efficient analytics both in production and technology centers, to standardize the way people access and visualize data, to capture, share, and retain knowledge, to face the ongoing generation change, and to enhance collaboration between experts. To translate these soft goals into a technical realization, we have implemented a data analytics architecture with the PI system as backbone. Every part of this architecture is mapped to a workflow step required to achieve our data analytics goals. Concretely, in the first step of the workflow, we measure what? Well, data from our sensors and controllers, which constitute the first level of the architecture. Then we collect. This information will be collected in local PI archives. In a similar way, we measure and collect information from simulation environments, MES systems, and soft sensors. As next step, we move and structure this data into regional PI archives with asset framework, where we standardize the data based on consistent naming and structural conventions. As next step, we monitor. How? Well, by means of asset and process AF templates provide us with analytics, event frames, and notifications. The next step is simulate, or more concretely, integrate the results of our online simulation environments with our process measurements, which allow us to detect deviations and therefore process anomalies. The next step is analyze and derive thereby useful insights from our data by incorporating self-service analytics tools And finally, we predict and generate process KPIs, forecasts, by means of machine learning and artificial intelligence tools that can help us to optimize maintenance and operational activities. The main outcomes of these steps can be then visualized in a one-stop shop visualization interface, namely PyVision, where we have developed a system navigation cockpit with standardized process and asset dashboards. I know at a first glance this architecture might be a bit hard to grasp. Let's break it into pieces for a better understanding. For that, I hand over to my colleague Philip.
Thank you, Esteban, and good afternoon from my side. Esteban just gave us an overview of our data architecture. In the remaining part of our presentation, we will dive into the steps of the workflow and will explain the components of the data architecture. Let's start with the very bottom of the pyramid, measure and collect. In our production plants, we have a lot of sensors and controller data. That data is stored in local Pi archives. These local Pi archives are geographically distributed around the world, usually very close to the corresponding production sites. Sometimes we need for our data analysis stuff other data sources like data from SAP, data from the lab, or simulated data. And you can imagine that it could be very complicated to connecting the different data sources and different local Pi archives, especially when every data source had its own workflow to get access to the data. So what we need is a kind of centralized data infrastructure and a standardized view on the data sets. And thanks to the support of our Pi experts we have luckily in the company, this was achieved by setting up regional Pi archives. And during the setup of the regional Pi archives, one key question was how to move and structure the data from the local Pi archives to the regional PIIF servers. And having in mind that every production plant and every site has its own individual history, especially regarding naming convention. Okay, the next step is move and structure. The first thing to do is to translate every tech name to the same naming convention. Because at the regional Pi server, every tech name should follow the same nomenclature. And we are using a nomenclature called FLOC, functional location. And this naming convention is based on 4 levels. We have the site and process, the process area, the process section, and then the tech name. Changing these names requires a high amount of effort, but it's definitely worth to do it, because then the second step is much simpler. And the second step is creating an appropriate tech hierarchy based on our naming convention. And it is much simpler because the parts of the naming convention can be mapped one-to-one to the elements or to the path, to the levels here in the tech hierarchy. And the result is a hierarchy that consists of all our PCT equipment, all of our sensors we have in the field. Of course, PCT equipment is only a subset of our assets. The remaining part of our equipment, are our assets. And with assets, I mean our unit operations, like distillation columns, pumps, heat exchangers, or reactors. Here we are using the same nomenclature, except that for the 4th level, we are using the asset name instead of the tech name. The result here is a second hierarchy, the asset hierarchy, that consists of all the main assets or all our main unit operations. And here, these elements are based, these are the unit operation, and these elements are based on AF templates. And we have developed AF templates for our most common unit operations we have in the company. Okay, at this point, we have 2 different hierarchies, the tech hierarchy and the asset hierarchy. How are these two hierarchies related to each other? To that end, you see on the left side the tech hierarchy, and here the elements function as data sources. On the right side, you see the asset hierarchy, and here the elements function as data consumers. And the connection between both hierarchies is realized in form of attributes defined in AF templates. And this connection between data source and consumers via the AF templates, this is our technical foundation to enable asset monitoring. And monitoring is exactly the next step in our workflow. Let's talk about monitoring. The situation is that we have lots of things to monitor. We have PCT equipment, we have unit operations, processes, and entire facilities. And how should a monitoring system looks like that provides information about the most important KPIs to do the monitoring stuff? And here we decide to go with PyAsset Framework. We are also using the analysis services. We are using event frames and notifications. And on the next slide, we will show you how we did the setup for such a monitoring system. You see on the left side a depiction of a very common distillation setup. In the middle, this is a distillation column. You see here at the bottom the reboiler. This is a condenser, and the feed to the column is preheated by a heat exchanger. This distillation setup is part of a plant with the name DDX, located in Baytown. The process area is V005, and the name of the process section is KF01. And exactly these names define the path in the asset hierarchy, and the elements here are the equipment we see here at these positions in the distillation setup. And we have templates for every unit operation we see here, for the column, for the reboiler, condenser, and the heat exchanger. And because this setup is really common in our company, the reusability of the templates is also very high, and this helps for the rollout and also to keep the maintenance effort low. Let's take a closer look into the heat exchanger template. This is a heat exchanger. Honestly, a very well-equipped heat exchanger because we have temperature measurements and flow measurements at both sides, at the utility side and the process side. And one challenge here is that only by knowing the name, for example, for this temperature, it's not possible to say, is this an inlet temperature, is this an outgoing temperature, is it on the process or on the utility side? Or another question is, what is the corresponding flow meter to that temperature here? Only by knowing the name, it's not possible. But by using the attributes in the PyIF templates, it is possible, because what do you do with the attributes? You add the meaning or the context to a PyTag. And exactly this functionality, adding meaning or context to PyTags, is very valuable for me as a process engineer. But this is not only but there are also other advantages. One other advantage is that by knowing the meaning of a PyTag, it is possible to do automatic calculations of KPIs. And one of the most popular KPI for a heat exchanger is the heat transfer coefficient, or the U value. The heat transfer coefficient is defined by a function as a function of two well-defined temperature differences and a flow meter. And the heat transfer coefficient gives you an indication about how easy it is to transfer heat from the hot side to the cold side. And therefore is also a good indicator for fouling. And thanks to the chemistry in our processes have fouling tendencies. So we see a decreasing trend over time in the heat transfer coefficient. Of course, it's nothing new to do fouling indicator calculations, but only by using the templates it is possible to do a rollout at a large scale. Another advantage is then when you can create event frames. For example, when the heat transfer coefficient is reached a certain level, event frame can trigger a notification to inform a maintenance engineer who can then schedule next cleaning activities. Yeah, so important the heat transfer coefficient to assess the performance of a heat exchanger is. It's not always possible to do this calculation because of missing instruments. But thanks to many colleagues, we have a lot of very accurate process simulation models in place. And we can use this first principle models to fill missing instruments. And Esteban will show you how.
Thank you, Philip. All right, so the next step in the workflow is simulate. More concretely, how we integrate simulation results from online models and process measurements. This integration is basically realized by integrating the readings of our field devices with the results of online process models. This allows us to increase the visibility we have of the process. The integration happens within our PyAF templates and can be visualized in our PyVision dashboards. Let me provide you an example of how this works. In the field, we have 5 temperature measurements to monitor the profile of this column. The blue points in this graph depict the respective values. The online simulation model of this column, however, computes temperature values for every column stage, providing us with 25 different values to monitor the profile. So you can see here the orange points in the graph. Note here how simulation allows us a better visibility of the function of the column by providing us values for those temperatures that are not directly measured. If the model is accurate enough, this could be a viable alternative to replace missing instrumentation. Now imagine here the potential savings when considering that an installed field device measurement can cost up to several thousand euros. Note besides that this integration allows us to detect deviations between measured and simulated variables, which may indicate process anomalies. In fact, we have extended this comparison concept to do some sort of process-wide monitoring. And this was achieved by developing tables in PyVision. The columns of these tables depict the current measured and simulated variables and their respective deviation. So by using a color multi-state, it is pretty simple to glance, or at a glance, to observe and sort process deviations. Now these process deviations could be mapped or coupled to event frames and be used to generate timely notifications. The question here is what to do once deviations have been identified. This takes us exactly to the next workflow step, analyze. Aiming at supporting our experts during troubleshooting, the architecture has been seamlessly integrated to third-party analysis tools. This integration happens within our PyVision templates or vision dashboards and allows our experts to move from monitoring PyVision to explorative analysis in third-party tools such as Seek and TrendMiner. This is as simple as initiating an on-demand self-service analytics session by only clicking a button in the respective dashboard. The initiated session will be pre-populated with all relevant attributes corresponding to this asset or process, and also offers an extensive set of processing algorithms that can be used to solve troubleshooting problems. Let me provide you 2 examples. Our experts detected an anomaly in one of our columns, and therefore they proceeded to conduct troubleshooting. By clicking the respective button in the dashboard, they initiated an on-demand session in TrendMiner and performed a simple pattern recognition to see if this behavior had been previously observed in the past. A few instants later, results were displayed. As a matter of fact, we had seen this behavior, and the root cause of the problem was quickly identified. In a similar fashion, our experts suspected a decaying behavior in the catalyst activity of one of our reactors. They accordingly initiated an on-demand session in SEEK this time by clicking the respective button in the dashboard, and only with few steps they could reconstruct the temperature profile of the reactor for several periods along the last 7 years. The generated view, as you can observe, allowed them to verify their hypothesis and generate a consistent and understandable report to experts and the management. While most common troubleshooting problems that our experts face daily can be solved with these sort of tools, there are some more complex troubleshooting activities that may require automated root cause analysis, scenario testing, or multivariate forecasting. These sort of problems can be best solved by using dedicated machine learning tools. This takes us to the next level of the architecture, Predict. In order to enable use cases such as predictive maintenance and process optimization, we have integrated in the architecture machine learning and artificial intelligence tools. An example of these tools is Fero from Fero Labs. This tool uses Bayesian machine learning to learn prediction models based on our Pi historical data. This is an example of one model created in Fero to predict a complex case of fouling in a heat exchanger, and these are 3 examples of the current tasks our experts perform with it. As you can see in the left side of the screen, the fouling behavior in this heat exchanger changes during different campaigns. Sometimes it's fast, sometimes it's slow. Although we run the plant at the same rate and basically with the same conditions. Our experts don't really understand why sometimes it's fast, sometimes it's slow. So one activity they perform is root cause analysis using the software. Fero automatically computes a factor importance report indicating the influence of different process variables over the fouling. This information is used to identify those factors with more influence and take counteractions to prevent fouling. The second activity is multivariate forecasting. Fero generates forecasts with associated confidence intervals, as we can see here. This is an example of a forecast for the heat transfer coefficient, which, as Philip explained us, is an indirect measurement of fouling. So these sort of graphs are used to plan maintenance activities on the heat exchangers. The third task is scenario testing. By using the tool, our experts can assess the impact of setting certain conditions on the influence factors over fouling. What I mean exactly? So they can ask questions of the type, what will happen with the fouling if we change this parameter in this way? You specify a condition, you see the effect on the target, in this case, the heat transfer coefficient. As you can see here, by performing this action, we could increase the heat transfer coefficient of the heat exchanger and continue operating. These are a few examples of how we use machine learning. Machine learning complements in this way our set of tools for monitoring and self-service analytics. As you can see, we have different options to analyze process behavior and predict what would happen in the future. Visualizing the results of this varied set of tools, however, can be overwhelming for some users. This reveals the need for a one-stop visual interface that can combine all those results. This is precisely the last component of our architecture, which Philip is now going to explain us.
Thank you. Okay, yeah, we have seen in the last slide that a lot of data is handled and generated by connecting different data sources, by adding information to existing data sets, or by simulations or calculations. But remember that the goal of the entire workflow is to assess or possibly optimize the performance of assets or processes. Therefore, it's important for the whole concept to have an easy and fast access to the data. And this is why we create a kind of, designed a kind of one-stop shop visualization consisting of a navigation cockpit to navigate through the information, through the data, and this, which also consists of standard dashboards based on the template idea for our assets and processes. The visualization concept was developed in PyVision, and I will show you a few screens to give you an impression how that can work. This is a landing page of our navigation cockpit, accessible via browser. Depending on your role or depending on your interest, you can select between different views. And for this presentation, we have prepared two views, the asset view and the hierarchy view. This is an asset view, and the idea behind the asset view is that you have a very quick access to all equipments of one kind at once. For example, all pumps, all heat exchangers, all distillation columns. And this is very important for our asset engineers who take care about the assets of the entire site, for example. And they benefit to have easy access to the important KPI to assess the performance of the assets. Thanks to the template idea, it is this list is always up to date. You have to create this visualization only once, and then this dashboard pulls information from the AF structure, so the maintenance effort is also very low. The second screen is the hierarchy screen. Basically, you can access the same information by both screens. The only difference between the few views is the way of navigation. Here, for the hierarchy view, the idea is to get information about the asset associated to one plant. And this is important for our plant engineers who take care about one plant. Okay, you have basically the same information by both views, and the endpoint of the navigation concept is always the standard dashboard for the unit operations. And I will show you one dashboard. This example is this is a visualization for a distillation column. You see on this side the distillation setup with the reboiler, condenser, and the preheater. You see some process variables, and on the left side you see the diagrams with the most important process variables, like the temperature, pressure, profiles, or the level of the column bottom. How can you work with such a dashboard? At the beginning, you see there we have relatively steady state operation, normal operation, everything is fine. A bit later, we see some hiccups. And typically, the process engineer have already a gut feeling what can go wrong. For example, one effect for a distillation column is called flooding. Flooding is when you have too much vapor in the column, and this vapor flow prohibits the liquid to trickle down. And when you have a flooding situation, the column is not able to do its job to separate a mixture. Okay, when you have the feeling, it could be flooding, we have here some pre-configured troubleshooting screens. So you can click on the flooding screen, and then a new diagram will open with pre-configured process variables that are necessary to assess, do I have a flooding situation or not? And we see here the same time range. At the beginning, more or less steady state, and then the hiccups. But with this time resolution, it's not possible to do any further analysis. So we click to zoom in, and instead of 1 day, we see now only 4 hours, and this is a good time resolution to see the effect. We start also with the steady state conditions, and then 2 things happened. The level of the column decreases and the pressure drop increases. The level is the level of the bottom vessel of the column. And the level decreases because the vapor prohibits the liquid to trickle down. The level decreases. At the same time, the pressure drop increases. This is the pressure drop along the column. And the pressure drop increases because our liquid hold up in the column increases too. And this is a very strong indication for a flooding situation in the column. The next question is, why do I have a flooding situation? Is it due to a high load, or is it due to fouling within the column? To answer that question, we see some further process variables that characterize the load of the column. And the green one is the inflow, and the purple one is the steam. And at the point in time when the flooding situation started, the load remains the same. And after the operators recognize that something goes wrong, they even reduce the load by stop the steam supply. And but by doing this, even the pressure drop still increases. So this is a very strong indication that we have flooding due to fouling and not due to the load. In this case, we came very quickly to that conclusion, flooding due to fouling. But sometimes it's more difficult. But even then, these screens are helpful because it's a kind of starting point for further analysis, for example, in the self-service analytic tools or machine learning tools, as the one mentioned before. Okay, this was the visualization concept, an example from the visualization concept as a last piece of our workflow. So we are almost at the end of our presentation. I will hand over to Esteban again, who will summarize and conclude the presentation for us.
Thank you, Philip. All right, so let's summarize the scope and benefits of ProDavis by comparing what we had before and after the project. Before ProDavis, our process experts were often confronted with difficult data access to local PI archives due to IT issues, different naming conventions, and in general, a lack of data context. Our solution was to provide them with a regional standardized platform based on asset framework where they can efficiently access the data and the context they require. Before ProDavis, our experts had virtually hundreds of island solutions for data analysis. Every expert had an Excel table with macros and Visual Basic code to perform calculations. Our solution was to provide them with a set of seamlessly integrated tools, both self-service and machine learning, where they can learn models, analyze process behaviors, and share their insights with other experts. Before ProDavis, our experts had limited options for data visualization. They used to rely in process books poorly maintained. They needed to install software and keep files in their machines to be able to visualize parts of the plant. Our solution was to provide them with a one-stop shop visual interface in PyVision, where we developed a navigation cockpit with standardized asset and process dashboards. Since then, they don't need to install any software. They can access the data simply by a web browser, and as the platform is centrally maintained, they know at any time that they are working with up-to-date versions of the dashboards. Satisfied with the current results of the project, Jane Arnold, head of Global Process Control Technology at Covestro, said, and I quote, "By exploiting the PI system, we managed to create a scalable data analysis platform that allows our process experts to visualize and analyze process data in an efficient fashion. Not only have we made it easier for them to turn data into valuable insights, we also have laid a robust basis for continuously harvesting from digital opportunities. Naturally, not all has been straightforward in this journey. Along the way, we have found several technical and organizational challenges, and we have learned some important lessons we would like to share with you to conclude this presentation. The first challenge was the large number of assets found in process industries. We found that we have hundreds of asset types in our processes. Modeling all of them would require a huge effort. What we learned while deploying AF templates is start by the most critical and common assets, those that really need to be monitored, and those that can be easily deployed based on templates. The second challenge was the high variability within asset types. We determined, for instance, or we found, for instance, that columns are critical and common assets, and therefore we need to monitor them. However, when we started the task of creating a template for a column, we realized that we have different column configurations and different properties. So the lessons we learned there is develop templates that are general enough to capture the most important asset characteristics. Keep it simple. Another lesson we learned there is create dashboards that are capable of dynamically adapt to the different asset configurations. Use vision multi-states and collections to avoid the need of creating several dashboards for the same asset type. Remember, we don't want to replicate the process books of the past. The next challenge was missing instrumentation. While deploying AF templates, we were really happy, or we had the templates, let's deploy. We realized that in many cases, we were missing instrumentation to be capable of properly monitoring the performance of our assets. If installing additional instrumentation is not an option for you, due to high cost, for example, explore the possibility of using rigorous simulation of soft sensors as replacement. Deployment was and is still a challenge for us. Certainly, deploying AF templates in different facilities around the world is a time-consuming task. What we have learned so far is that by partnering with third parties, it is possible to automate part of the deployment process and guarantee consistent system maintenance. Finally, and more in the organizational aspect, we found some resistance to digital transformation. What we learned in this aspect is involve stakeholders from the very beginning. Listen to their pain points and propose useful painkillers. Explain to experts that the new technology is not there to replace their past efforts, but rather to support them. Show simple but concrete use cases with added value. Explain management how they can easily profit from the new technologies. And the final tip is do dissemination work. This is a point we have been working in, and we will continue doing so in the future to bring data and data analytics possibilities to as many people in the organization as possible. With this, we conclude our presentation. Thanks a lot for your attention.
Any questions for Esteban or Philip? Come on, it's after lunch. Everybody should be awake. So I did have a question around the self-service analytics. Great use of not only PiVision, but also our external partner technologies. How do you decide between one and the other and what to use between PiVision and say, Seek, for that example?
This is a great question. Actually, we have explored both of them as alternatives for self-service analytics. They are both really good at that. Some functions might be better in one, some functions might be better in the other. Typically, you could solve the same problems with both. The only difference is you will follow a slightly different workflow. We can tell you which one is better. It's up to you to test them and find that by yourselves. You can just say that both are really good pieces of software.
Along those lines, the link that you followed to go from PiVision outward to Seek, the Seek display, is it pre-built?
Correct. That is our dashboard for visualizing an asset or a process. Basically, that asset will generate an URL, and this will open a session in the third-party tool, right, either Seek or TrendMiner. And by default, this session will be pre-populated with all attributes for that asset, leveraging the asset framework. So basically, we just go to the asset framework and collect all the information that is available for the asset and make it available on Seek or TrendMiner.
Thank you. Any more questions? Going once, twice. Gentlemen, thank you very much.
Thanks.
Yeah.